Hello again. So today we are going to be doing a video on this circuit which we have right here. What this circuit does is it's basically an analog motor controller. I am controlling a DC motor with a feedback potentiometer using only op amps, and that gives me an analog way to control a motor. What I could do is I could move the potentiometer, and that will cause this motor right here to move. The whole circuit is off right now, but we are going to turn it on. So this is a prototype robot arm for a project that I'm doing involving a robot arm. We have these servo motors right here. You can see these are servos on the wrists. Servo motors are very easy to deal with. They are controlled simply by a PWM signal. They will position themselves based off of that signal. But the problem is, with a big robot arm like this, you're going to need a lot of torque, and that's a lot more torque than these little servo motors can handle. These give you about 7 kilograms per centimeter maximum. This gives you like 70. But the problem with this is that it doesn't position itself, so we have to have a potentiometer right here on the other side to give us feedback. Alright, so now we have that. Now we have to position the motor based off of the feedback. So there are many ways you could do that. Probably the most easiest and simplest or whatever thing you're thinking about right now is using an Arduino or whatever. But I don't really want to do that because I've already tried that and I've done it and it works, but this seems more interesting. Also, these op amps are way less expensive. So there we go. We can look at this actual circuit and how it's laid out. So coming off of this motor right here, you can see that the power wires go down and they go into this L298 basic DC motor controller. So this motor controller has several pins on it. You have power coming in, a common ground, and 5-volt out to supply the controller. And for the control pins, we have enable, which enables the motor. You can also apply a voltage here or a PWM signal, and that allows you to control the speed of the motor, which is pretty important. And then these two pins just control the direction. So next we move on to the circuit, which actually positions the motor. So to actually understand what's going on in this circuit with the messy wiring aside, we have to look at this document that I wrote right here. The motor controller is a proportional controller, which means that the proportional control means that when the motor is closer to the set point that it needs to be at based off of this potentiometer, then the motor will slow down so it doesn't overshoot the set point and jitter. So that's pretty important. So how this is accomplished is via these two kind of parts. So for this first part of the circuit, we have the set voltage and the feedback potentiometer. This is set up as a comparator. So if the feedback potentiometer is greater than the set voltage, then the response is going to be to retract. This means that we are above the set point and we have to go back towards the set point. And of course, in the opposite case, when the set voltage is greater than the feedback potentiometer voltage, that means that the output is going to get inverted, which means we have to advance the motor because we're currently below the set point and we have to move to the set point. So this just determines the direction of the motor. As we said, we want proportional control, and that's handled by this circuit right here. One thing that I really made a point not to do is to not have to use negative voltages, because if you had a negative voltage supply, you could get away with just using one of these op amp subtractors, and that will tell you, oh, if it's in a negative position, then you got to go back to the positive. If it's in a positive, go back to the negative. But this right here just gives you the absolute value. That is how far the motor is away from the set point. These two are subtracting amplifiers. That means that one of them is subtracting the feedback potentiometer voltage from the set voltage, and the other one is subtracting the set voltage from the feedback voltage. Since there's no negative supply, that means that if the answer to this minus this is below 0, then it won't work. So we have to have another amplifier that does this minus this, and that will give you the positive output. And they both come together with diodes, and this gives you roughly the absolute value of the proportional control, and that goes to the enable pin on this board. So again, this is just kind of what I said. So the comparator determines the direction, and proportional control is handled by these two subtracting amplifiers. So now we can look at the circuit, and this makes a bit more sense. So this is the comparator, and these two are the subtracting amplifiers. These two LEDs are to extend and to retract based off of the comparator, and these three LEDs represent the three outputs, which is proportional control in one direction, which is this one, proportional control in the other direction, which is this one and this one, this LED, and then the absolute value proportional control, which actually matters, is this one right here. This is the one that's actually used. Additionally, there's this part of the circuit. I'll explain that at the end of the video, but it's basically to determine integral so we could have a proportional integral controller, and this isn't hooked up right now. So I think now we can demonstrate the actual circuit being used. Alright, so now we have everything is turned on, and we can actually position this motor based off of the potentiometer right here. So we could go in, and we could go out. And this allows us to get the full range that this motor can do. But we can go that far, and we can also go back to the set point. We can move really fast, and we can move very slow as well. So right now we're just moving it basically as fine as it will go. So as you can see, when this LED is green, it's going to move out, and if we want to move in, it's going to be red. The next step in this is, if we want to actually make a robot with this, we would replace this potentiometer with a control voltage from whatever microcontroller or input that you're trying to actually move the motor with. But right now we just have a potentiometer, and that allows us to have the motor mirror the position on the potentiometer. So now I've turned off the lights, and it should be much easier to see these LEDs. So extend outward, extend inward. As you can see, this green LED is correlated with proportional control for this one. So this is the direction to move the arm out, and this is the proportional control to move the arm out. So as you can see, when this gets big enough, the motor will move out, and that will reduce the error. Same thing for the inward one. If we move in, so now it has to go in, but the proportional control to go in is too low. You can see it's kind of right on the set point right now, as the green LED flashed a little bit. If I move it just a little bit, then this LED will light up, and it will move in. And this right here is the absolute value of the error. No matter if this one or this one is on, this one will be on as well. So as we went over, this whole circuit is a proportional controller. Well, that's not exactly the complete picture, as we would want a proportional integral controller as well. The integral is important because, as you can see, this LED is on. But right now, the actual error is too low to make the LEDs light up, but there's still error. So it's not exactly on the set point, it's just very close. But though it's not exactly on the set point, the error is so low that the motor can't move. So it wants to move in this direction still a little bit more, but it can't. What I'm trying to do right now is to make a integral controller. that will be summed with the proportional controller so that the motor can more easily move to the set point. So what the integral controller does is it basically says the longer the error persists, then the integral term will get bigger, and hopefully it will go big enough so that the motor will actually move back to where it's supposed to be, towards the set point. So I haven't made the integral controller yet, but I have made part of it right here. So essentially what this does is these two op amps will charge their respective capacitors while there's any error at all. So this is a comparator with 0. So it's basically acting as a buffer, and it has to be a buffer so that these two are separated from each other and they don't mess with each other. Additionally, we have these two MOSFETs, and these drain the capacitor. So the op amp will charge the capacitor when there's any error at all, which is pretty much all the time, and the MOSFETs will drain the capacitor when the error is in the opposite direction. So as you can see right now, there's green error, so that's causing this capacitor to drain, which is causing this LED to be off. But with the opposite direction, since there's no red error right now, that means that this capacitor is allowed to charge and it is on. So what we want to do is to use the value from this LED to be used as the integral control, so that if this wants to move outward and this LED is saying, no, we don't have enough power, that eventually after enough time, there will get enough charge in this capacitor that the motor will actually want to drive outward to the set point. All right, so let's say we have error in this direction. What that's going to happen is this LED is going to discharge because it's being discharged by this MOSFET, and this LED is going to charge at this capacitor. And of course, this value could then be used to make the motor move inward. I haven't had this hooked up yet because I would have to sum it with the proportional control, which, as we had determined, is absolute value. This is only for either direction. We have to have it so there is an absolute difference error. If we have to move in the green direction, this LED is going to discharge and this one's going to charge. Well, what we really want to do is, while these two are both on, while this one's discharging and while this one's charging, we want to have the absolute integral error to be these two subtracted from each other, and add that to the proportional error. Getting the integral error working is going to require a lot more circuitry, and I don't really want to do that right now, but I thought I'd just explain it right here. The proportional error seems good enough for the robot that I'm making. We don't really need a precise control, and just using 3 of these op amps is more than enough for each motor. And I'm gonna have a lot of motors. Like, you could see this arm has like 3 of them, and it's just an arm. Yeah, so I think what we have right here is good enough. Also, here's the information for the integral thing. If we have error in the red direction, that means that the capacitor, which is drained by the green direction, will charge. And if we have error that's in the direction of the green LED, that means the capacitor drained by the red LED will charge, and that will give us the output. So this is the circuit that this part is. As I said, it's not hooked up. So yeah, here's my circuit on the proportional controller using op amps. Thank you for watching.